Welcome to Schmashapur. This video is for those of you who may be interested in math, but are not really familiar with how mathematicians phrase things. I want to introduce to you several words and phrases that mathematicians use that either mean something different from what they mean in everyday language, or are used in situations that don't come up that often outside of math, and so can be confusing if you're not familiar with them. This is not a video on mathematical terminology. The words and phrases we're going to see are not specific to any particular area of math, but commonly used by mathematicians in all fields. Our first word is or. Mathematicians usually use this to mean and or. That is, if I say it's raining or windy right now, it could be that it's raining, or that it's windy, or both. Mathematicians might also use or when they know which of the options holds. So they might say it's raining or windy right now, even when they know it's, say, windy, but not raining. If you're not used to this, it might sound a little silly. Now, that doesn't mean mathematicians go around saying things like this for the sole purpose of being unhelpful. Usually, we wouldn't do so without good reason, but I want to point this out because these good reasons tend to come up more often in math than you might think. As an example, let's suppose, for the sake of argument, that everyone who owns a cat or a dog buys pet food, and that John owns a cat. And someone asks you, does John buy pet food? Maybe the answer seems obvious, but let's go through it one step at a time. Since we know John owns a cat, we can safely say that John owns a cat or a dog. And since we said everyone who owns a cat or a dog buys pet food, we can conclude that John buys pet food. But in order to get there, we needed to pass through John owns a cat or a dog. Even though we're not in doubt, we know John owns a cat. The point is, we may need to pass through seemingly unhelpful statements in order to get to something meaningful. Our next word is if. When I say, if Alice is coming to the party, Bob is too, you may be picturing that Bob is waiting to hear if Alice is coming to the party, and if he hears she's coming, he'll come too, but he'll stay home otherwise. But to a mathematician, this means perhaps Alice and Bob are both coming to the party, or Alice isn't but Bob is, or neither of them are coming to the party, but it certainly isn't the case that Alice is coming but Bob isn't. This is different from the colloquial version in a few ways. First, the colloquial version suggests some sort of causation. Bob's decision depends on Alice's. But the mathematician's version does not. In fact, whereas here we can talk about causation because it's a statement about the real world, there is no causation in math. One mathematical statement being true doesn't cause others to be true, they just are true, or they're false, to begin with. In our example, it could just as well be that Alice is basing her decision on Bob's, and will choose to stay home unless she hears that Bob is coming. If Alice is coming, it must be she heard that Bob is coming, so we can safely say that Bob is coming too. If Alice is coming to the party, Bob is too. Also, the statement only says something about what Bob will do in the case where Alice is coming to the party. It says nothing about what Bob will do if Alice doesn't come. If we did want to claim that either Alice and Bob are both coming or neither of them are coming, we would say Alice is coming to the party if and only if Bob is. But let's get back to our previous example. Here, even if Alice says she's staying home, Bob might still choose to go to the party anyways, based on other factors. In fact, it could even be that Bob was always planning on going to the party regardless of Alice's decision. It might seem a bit strange to say this sentence when you know Bob is coming, and it has nothing to do whatsoever with whether Alice is coming, but this is similar to how we might use or, even when we know which of the options holds. And again, there are occasionally good reasons for phrasing things this way. On that note, it could even be that Alice is planning not to go to the party, regardless of Bob's decision. There doesn't necessarily need to be even a chance of Alice coming to the party in order to say this sentence. Actually, mathematicians like these if-then sentences and have many other ways of phrasing them. I won't go through a whole list, but I'll introduce another one that might be a bit confusing. This is our next word, implies. We can rephrase our previous sentence as Alice coming to the party implies Bob is coming, meaning the same thing. In everyday language, implies means something like suggests, but here it's a lot stronger. It means it is certainly not the case that Alice is coming but Bob isn't. Next, we have all or every. In math speak, if I say something like, all unicorns in this pasture are blue, I'm not claiming that there are any unicorns in the pasture. All I mean is that any unicorns that happen to be in the pasture, should there be any, are blue. You'll never be able to find a unicorn there that's not blue. But it might happen that there aren't any unicorns in the pasture, in which case it's still true to say that all unicorns in this pasture are blue, or pink, or whatever we want. We say these statements are vacuously true. Next up on our list is some, as in some ravens are black. To a mathematician, this doesn't necessarily mean that there are also some ravens that are not black. It could be that all ravens are black, but at least some of them are. Now, I find using some like this a little confusing for a different reason. The plural seems to suggest that there are multiple ravens that are black, but it's more common in math to want to claim that at least one of something exists, rather than at least two. We can phrase this instead without the plural as some raven is black, but my preferred way to phrase this is there exists a raven which is black. In either case, we're not claiming that there is necessarily only one black raven. There could still be multiple black ravens, but we know there's at least one. Next, we have in general. Colloquially, we can say, in general, basketballers are tall. What we mean is that while there may be some short basketballers, usually basketballers tend to be tall. But the way this phrase gets used in math is very different. When we say in general in math, we mean in every single case with no exceptions. So we would only say, in general, basketballers are tall if every basketballer is tall. Next up, variables. Mathematicians love to give things names in order to keep track of which they're referring to. These names tend to be short, often just a letter. These could be uppercase letters, lowercase letters, letters with various markings like subscripts or tick marks, or letters in other scripts, say Greek letters. Let's say we have a sentence like, each of my classmates knows someone who likes to braid their hair. The there in this sentence is ambiguous. It's not clear whose hair the friend likes to braid, their own or the classmates. We could clarify with, each of my classmates knows someone who likes to braid their own hair, or each of my classmates knows someone who likes to braid that classmate's hair. But epithets like this can still quickly get confusing. It's easier to figure out what the sentence means if we say something like, each of my classmates, say A, knows someone, say B, who likes to braid B's hair, or A's hair. From now on, we'll assume we mean the latter. If Henry is one of my classmates, this tells us that Henry knows someone, perhaps Rebecca, who likes to braid Henry's hair. The letters don't need to have anything to do with the things they stand in for. In this case, A stood for Henry and B for Rebecca. Also, even if we use different letters, they don't necessarily stand in for different things. It could be instead that Henry likes to braid his own hair, where the person Henry knows who likes to braid his hair is himself. Here A and B both stand for Henry. On a related note, counts. If I say 5 people went to the store yesterday, you might interpret that as exactly 5 people went to the store in total yesterday, or as there is a group of 5 people who went to the store yesterday. Perhaps others went too, but we're not focused on them. A mathematician could mean either one of these, depending on the context, and it's usually best to specify exactly 5 people went to the store yesterday, or at least 5 people went to the store yesterday. But what you probably don't mean is that the same person went to the store 5 times yesterday. For a mathematician, though, this wouldn't be so unreasonable an interpretation. Okay, maybe not in this example. But let's look at a mathematical example where an interpretation like this actually makes sense. We might ask, what numbers are the sum of 2 perfect squares? A perfect square is a number which is the product of a whole number with itself, like 4, which is 2 times 2, or 9, which is 3 times 3. So for instance, 13, which is 4 plus 9, is the sum of 2 perfect squares. But we also have that 8 is 4 plus 4. So 8 is also the sum of 2 perfect squares. You might complain that 8 is actually the sum of the same perfect square twice, but this still counts. The 2 perfect squares in question don't have to be different from one another. If we wanted to specify that the perfect squares had to be different, we'd say the sum of 2 distinct perfect squares. Thanks for watching. I hope this helps you better understand mathematicians.